Suppose we have the function f of x equals 1 minus x e to the x divided by x plus e to the x. And we want to take the derivative of this. We want to find f prime. Looking at the overall structure of this is clearly a quotient, so we should apply the quotient rule. As I mentioned in a previous example, we could force that into the form of a product, but it gives us some additional structure that we don't have the tools to deal with easily at this point. So the easiest thing to do with this is to leave it in the form it is, deal with that as a quotient. So the quotient rule tells us that we want to take the derivative of the numerator multiplied by the denominator and subtract the numerator multiplied by the derivative of the denominator. And all of that is divided by the square of the denominator. Okay. So let's start working some of this stuff out. We have the derivative of 1 minus x e to the x. Okay. So we can differentiate each term individually. We have the derivative of 1, which is 0, minus the derivative of x e to the x. Let me come back to that. So for right now, I'll just write the derivative of x e to the x. And now we'll copy the parts that haven't changed. So we have times x plus e to the x minus 1 minus x e to the x times the derivative of x plus e to the x. So again, we differentiate term by term. The derivative of x is 1. The derivative of e to the x is e to the x. So we have 1 plus e to the x there. All over x plus e to the x quantity squared. Now, why did I postpone taking the derivative of x e to the x? Well, that is a product of two functions, isn't it? We have the negative of the derivative of a product of two functions. That means we need to apply the product rule. That'll be the derivative of x times e to the x plus x times the derivative of e to the x. Right? And that was all just taking the derivative of that first part there. That is times x plus e to the x minus, let's see if I can squeeze this in without losing too much legibility. If this is hard to read, it's the same as what's on the previous line. I haven't changed anything else at the end just yet. So the derivative of x is just 1, so we have 1 times e to the x, plus x times the derivative of e to the x. The derivative of e to the x is e to the x. So now, finally, at this point, we have evaluated all of the derivatives. So what we're left with is technically a derivative of the function that we were asked for. However, this is a little bit beastly, right? We would probably rather not leave it like this. That's kind of a mess. So let's see what we can do about cleaning some things up a little bit. Let's start distributing. So it looks like we will have negative x e to the x minus e to the 2x minus x squared e to the x minus x e to the 2x minus 1 these first four terms were from foiling this. Now we'll FOIL this out. We'll distribute those. So we have minus 1 minus e to the x. This would be a negative x e to the x, but it's minus that, so that is plus x e to the x. And plus x e to the 2x. All over x plus e to the x quantity squared. Now let's see if there's anything we can simplify. Hopefully there is. We have a whole bunch of negative terms and a couple of positive terms. We have a positive x e to the x, and here we have a negative x e to the x, so those add up to 0. We have an x e to the 2x and a negative x e to the 2x. Those sum to 0. And it looks like, is there any particular order to write this in? Not really. They're all negative. We have negative e to the 2x minus x squared e to the x minus 1 minus e to the x all over x plus e to the x quantity squared. And it looks like that is about as simple as that gets. Unless you would rather have fewer negative signs. Of course, you could factor out a negative to the front and make the numerator all positives, e to the 2x plus x squared e to the x plus 1 plus e to the x over x plus e to the x quantity squared. That would be another way of writing that if you wanted. Again, neither of these is really simpler than the other. It's just a matter of whether you would rather have a negative sign out front or just as simple a fraction as possible. Looking at the structure that we have here, this doesn't really look like it's going to factor nicely. And in particular, we doubt that x plus e to the x is going to be a factor, especially because of this term of 1 here. If we expand the denominator, anything that's not a fraction that we multiply x plus e to the x by is not going to get rid of either of those and reduce down to 1. So we know that this is not a factor. There's nothing to be gained by expanding or trying to factor this. That is about as simple as that one gets. So this was a little bit messier because we have a quotient, and inside of the quotient, part of that function was a product. So in the course of evaluating this, we had to apply the product rule when we got to that. So you can see why I've been very careful to write out the differentiation operators as I go through to make it very clear what we need to take the derivative of and what has been taken care of, that we don't need to differentiate any further, and stepping through that step by step. Of course, if you are comfortable enough with these things, you could always say, from the original function, which was 1 minus x e to the x over x plus e to the x. If you do not find it helpful to write differentiation operators, if you can keep track in your head of where you aren't required to, right, as long as you're taking the derivatives correctly. So you could always say, derivative of the top is going to be negative, and I will write one derivative operator here just so I remember to come back. Actually, you know what? I don't need to do that. Just to illustrate, I'm not recommending you do this until you're well practiced. Make sure you do lots of exercises. But you could always, if you really wanted, say, okay, when we differentiate the top, we're going to get an e to the x plus x e to the x when applying the product rule in that, and then that is times the bottom minus the top times the derivative of the bottom all over the bottom squared. And you see that what I've done here is I've gotten to where all the derivatives are taken care of, and then it's just algebraic simplification. I would still, of course, have to multiply this all out and combine and simplify. This is not done. We have simplification to do. But it's, once you have done enough of these exercises, you may find yourself able to skip some of those steps. but you can. I often qualify this, and you can probably hear it in my voice. Every time I talk about skipping steps, I'm a little bit nervous and a little bit cautious because I know there's a natural tendency to want to write as little as possible, and I'm right there with you. Most of us mathematicians are lazy. We try to do as little as possible to get our work done. But, the human brain only holds a certain number of things in working memory at once. And especially the less familiar you are with things, the harder it is to keep them all in mind at once. So I do not recommend that you attempt to do this actively. Instead, you should begin by being very careful about notating your derivatives and what you're taking the derivative of when, and evaluating those step by step. And as you go, you will naturally discover that with sufficient practice, you will start discovering that, well, you don't need to write this, you know what it's going to be, right? And only at that point should you stop writing those. The only reason I mentioned this was to say, I'm not going to require that you absolutely write every single differentiation operator. Once you're practiced and you don't need that, that's fine. But do make sure that you're very careful. And again, when in doubt, write a little bit more than you think is necessary, particularly in case you make an error. All right, there's a whole lot of algebra going on here. So even those of us who are very experienced can sometimes make a mental oversight and make an error as we're working on something. And if you make a mistake, you want to make sure that whoever's grading your work can figure out what you were trying to do. And that's usually easier if you have written more steps than written too few. So again, when in doubt, write things down. But if you find yourself in a situation where you see absolutely no point in writing a particular thing, as far as some of these intermediate derivative steps, it's fine, you can get a step over those. Do make sure, though, that there is, of course, sufficient record of what you have done. Right? So something like this still has the quotient rule structure to it. And somebody who is experienced with calculus can look at this and see what went where, right? They can see that 1 minus x e to the x produces this derivative, and that x plus e to the x produces this derivative, and figure out what things are doing. Do not try to combine that step of differentiation with a step of algebraic simplification. If you're doing so much in your head that you try that, first off, that's much more dangerous. And secondly, it makes it much harder for a person to read and figure out what you're doing. Try to keep to one clear type of operation per step, right? You'll note that I did practically no algebraic simplification here. All I did was I took some derivatives, and then any algebraic simplification I would do would come in the next step. So try to separate those and make them as clear as possible. But yeah, so you can see that things like quotient rules and product rules can be nested inside of each other in various ways that can become increasingly complicated. You can just keep stacking quotients and products inside of each other. Don't get overwhelmed. Just take it step by step, piece by piece. Especially at the beginning, use the notation to clearly document for yourself what do you still need to take a derivative of, and organize all of that as you go. But hopefully that makes some amount of sense there.